So before we head into uh, looking at some definitions for additional trig functions, let's take another look at our graphing for sine and cosine. And let's remember, we want to graph the sine of theta versus or onto theta. And so if I consider over here my angle in standard position, theta in standard position, as theta increases positively, and we're going to think about it in terms of radians, the sine is the y-coordinate, and I begin at 0, and that y-coordinate increases, and if this is the unit circle, it heads to 1 when I get to pi over 2. And it increases pretty quickly at first. The y-coordinate goes up pretty quickly, and then it slows down, growing as theta gets closer and closer to pi over 2. So I start with my y-coordinate of 0. At 0, I grow pretty quickly at first, and I slow down as I head and approach pi over 2, and I get up to 1. And then again, what happens is I continue down. As I continue, as theta increases, my terminal side continues to spin. As theta increases, my y-coordinate from pi over 2 to pi is going to head down from 1 back to 0. It's going to go down slowly at first, and then it's going to go down more quickly. So again, back up here, I head back down to 0 when I hit pi. Then what continues to happen at pi, I then continue to terminal side spins along, and my y-coordinate heads down to -1. And that's at 3 pi over 2. And then what happens for the last little bit is I head up and get back up to 0 at 2 pi. So back up here at 2 pi, I get back to 0. So that gives me one period of the sine function. And note then, when I've gone the 2 pi around, I will start and repeat those values again, so I then know that obviously this graph is periodic, is going to continue out. Every 2 pi units will repeat. And remember, if I spin in the other direction, if I spin theta to be a negative measurement, I also am going to repeat that period here on the other side. So that's the sine graph. By the same reasoning, you can do the cosine graph. Looking at theta at 0 radians, my x-coordinate, which is the cosine, is 1. So the cosine graph at theta is 0 radians is going to start at 1. And then as you do the same process we just did, it's going to go down and repeat over the 2 pi units. And that's going to give you a period for the cosine graph. And one thing we might wonder, and we're going to look at in the future a little bit, is are the sine and cosine graphs the same shape? And if you think about it, you might see that perhaps I'm going from a high of 1 down to a -1, back up to a 1. And if I were to continue that sine graph along a little more here, I would start at one point here at pi over 2. I'd start at 1, go down, and come back up to 1. And it looks like I've done that by moving. If I move over here right pi over 2 units, it looks like I see that same shape. And indeed, a sinusoidal wave, the sine and the cosine are identical. It's just that one is a horizontal translation of the other. So that's again a little review on our sine and cosine, basic sine and cosine graph. And again, you want to know these shapes. You want to be able to quickly sketch a sine graph, one period from 0 to 2 pi with absolutely no thought. But at the same time, the thought, you want to go in and understand why that sine graph is what it is by thinking back on what that terminal side does for theta, and what that x-coordinate for the cosine and what the y-coordinate for the sine does, and how these graphs indeed are generated. Know them quickly, but also know where they came from. So we have briefly talked before last week a little bit about the co-functions, or the other, we talked about sine, cosine, and tangent a bit in class, and then we talked about 3 other reciprocal functions that again are just definitions that are trig functions associated with an angle theta, and the ratio created by either some combination of an x and or y coordinate of the point on the terminal side of the angle that intersects, in general, a circle of radius r. We saw it was, to graph the sine and cosine function, we saw that it was great to let r be 1. It made our computation simple. And we talked about the fact that if you were to draw any circle in here by similar triangles, your ratios of y over r are always going to be the same, or x over r are always going to be the same. So by definition, we knew that sine was y over r. We knew that cosine was x over r. And we knew that tangent, again, this is all by definition, is y over x. We have three other trig functions which are reciprocal, simply reciprocals of those ratios. So cosecant is going to be r over y. Secant is going to be secant is going to be x, r over x, and cotangent is going to be x over y. And those are definitions, and they do need to be memorized. Simple definitions, but again, you want to keep straight which one is which. So while our calculator has buttons to calculate, give you a decimal approximation for sine, cosine, and tangent quickly and easily, with the key being to make sure that you are in the right mode. Remember, if your calculator needs to know, are you working in degrees or are you working in radians? And again, important, if there's a degree symbol, obviously it's degrees. If there's no degree symbol, that implies you are in radians. So the question is, how would I use my calculator's sine, cosine, and or tangent buttons to find out how, what secant of 2.1 or cosecant of 123 degrees is? And the key is you got to use your definition, the reciprocal definition, for your trig values to do so. To find the secant of 2.1, the secant, you'll remember, is r over x. So if that's r over x, if I look at 1 over x over r, those are equivalent. And 1 over x over r would be 1 over the cosine of 2.1. So in other words, to get secant to be able to get a decimal approximation with secant, I've got to use that reciprocal relationship, which is 1 over cosine is secant, or 1 over secant equals cosine. For cosecant, ditto. I'm looking at cosecant as reciprocal relationship is the sine, so this would be 1 over sine of 123 degrees. And you want to make sure, again, that you've got that mode, you've picked the proper mode. Every time you're going to input a trig expression that you're looking for decimal approximation for in your calculator, ask yourself, are you in the right mode? And this is going to be important as we head into graphing of trig functions. In general, we're always going to graph in radian mode, in general. But occasionally you might be asked to graph with the degree mode, and you want to make sure, hey, am I in the right mode? The problem I'm working on in context, have I picked the mode with my mode button as radians or degrees before I continue? So let's take a look at, see if we can sketch a graph of the tangent function. That is, we're going to graph tangent theta versus theta, or tangent theta onto theta. And so again, my input is theta, and I'm going to view theta with an image. I've got in my mind the idea of that terminal side of an angle spinning counterclockwise around, the angle's in standard position, and I'm going to want to be looking at what's going on with a ratio here of y over x, which is my tangent ratio. So I look at that for a minute and say, let's see what happens. If I'm at 0, if theta is at 0, y is 0, and x is 1, so my tangent at 0 is 0. Now what happens as the angle spins around? Let's see, y is increasing toward 1, and x is getting smaller toward 0. And there's a point here right in the middle, obviously, where x and y are going to be equal. And you can probably visually see that that's going to be at pi over 4, or in other words, where y equals x here. and that's where the tangent ratio is going to be equal to 1. So I should be able to see at pi over 4, I'm going to get a 1. And then what happens is I keep going. Well, what's the limiting factor? As I come up here toward pi over 2, the y-coordinate's getting closer and closer to 1, and the x is getting closer and closer to 0. And the question is, suppose I've got this y over x, and I've got a number pretty close to 1, a little bit under, and I've got a number that's very, 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 very tiny. The closer that theta gets to pi over 2, the smaller the x-coordinate gets, the smaller that denominator is going to get. What kind of number is a number close to about 1 over a very tiny number? And the answer is a very huge number. And the closer I get to 0 radians, the bigger I'm getting. So in other words, at pi over 2 over here, the closer and closer I get to pi over 2, I'm blowing up toward infinity, and that's going to give me an asymptote here at pi over 2. And you can ask yourself, well, what happens if I went in the opposite direction? What happens if I spun here down toward negative pi over 2? And I'm going to get the same thing happening except with a negative sign. So again, at negative, as I approach negative pi over 2, my x-coordinate is approaching a very tiny number. My y-coordinate is approaching approximately negative 1. So I'm going to get blowing down towards negative infinity here as I approach pi over 2. And as I come up, I'm going to hit 0, 0. And I call this the tangent snake. Tangents and cotangent graphs are snakes. They do have asymptotes. And again, that should make sense. Look at what's happening at multiples of pi over 2 or 3 pi over 2. Your x-coordinate is 0, and in the tangent y over x, you would have a 0 in the denominator. That can't happen, and that's going to give you those vertical asymptotes. So, looking at your text on page 284, you can do the same reasoning and continue and see what's happening from pi over 2 to 3 pi over 2, and vice versa from negative pi over 2 to negative 3 pi over 2. You're going to create these rising snakes, these snakes that rise from left to right for the tangent graph. Periodic? Yes, definitely. The period for tangent is different from the period for sine or cosine. Tangent graphs repeat every pi units. So that's your tangent graph introduction. So your textbook shows you a quick introduction to the secant graph on page 284, since they do that there. I'm going to look at a quick introduction to your cosecant graph. Let's remember that the cosecant is the reciprocal of sine. So if your sine's y over r, your cosecant is going to be r over y. So basically what I'm looking to do for cosecant is, if I consider up here the sine graph, and I then say, well, what's the reciprocal going to be of all my y outputs? Well, clearly the reciprocal of 0 is undefined, and I'm going to create these asymptotes here every pi units for the cosecant graph. And then it remains to be seen just to say, okay, you know, at pi over 2, you have an output of 1. The reciprocal of 1 is 1. Ditto for 3 pi over 2. The reciprocal of negative 1 is negative 1. And then you just need to figure out what's happening in general and sketch in the other values. And you can see that, for example, as the reciprocal of a very tiny number is going to be a very large number. Ditto here. The reciprocal of a very large negative number close to 0 is going to be a negative number heading toward negative infinity the closer I get to 0, and ditto on the other side. So then you can sketch in and see that your cosecant graph is going to consist of a series of arches that repeat every 2 pi units. One of those arches is going up, and it's not a parabola, it's a cosecant graph. Yes, it is symmetrical. It does have each of the arches has a line of symmetry, but they're not parabolas. They're cosecant graphs and cosecant arches. And so I will repeat every 2 pi units. And again, do you want to memorize the cosecant or secant graphs? I don't. I choose not to. I get them every time I need one of them. I'll get it from looking at a basic sine or cosine graph and simply getting my reciprocal relationship, and then I would erase my sine or cosine graph that I used. So there's a quick introduction to your cosecant graph.